He is the CTO for the cloud-based analytics firm Elysium Consulting. Previously, Mike led the LA Solutions architecture team for Amazon Web Services and has a proven record of helping organizations around the globe launch massively scaled systems and services. Today, Mike will discuss strategies for blending front-end MPP warehousing with back-end data lake objects, object storage via AWS Redshift and Amazon S3. He will be presenting a talk titled Extending Analytic Research from the warehouse to the data lake. Please join me in welcoming Mike.
Thank you. Good afternoon. Thanks for joining. This is, I believe, year 3 or 4 of supporting this event, so I'm happy to see the audience size is getting bigger, more passionate. Thank you again for taking time out of your lunch break or maybe just after lunch to join. Again, my name is Mike Limcaco. I am the CTO for Elysium. It's a play on words between Agile and Elysium. We could have a beer over the naming of that. But happy to be here. Prior to joining Elysium, I focused on LA clients, on LA enterprises, large enterprises, in helping them design and develop innovative approaches to address their data challenges. So the goal here is to continue that focus, that hyper-focus, continuing to elevate innovation and provide that to clients and consumers. And so today we're going to talk about some of those best practices as it relates to extending the reach of the enterprise data warehouse, not to be left out of the whole data lake conversation. We'll talk about real-world implementation patterns to address this challenge. Let's talk shop. Let's dive right into it. And let's start with the premise that most data in the enterprise is dark. The concept here is, and if you do your surveys and do your studies and do your research, or even gather your feedback from your clients and consumers, you'll understand that the growing trend is to collect even greater amounts of content and data, whether it's through web, mobile, IoT, connected devices, sensor and telemetry data. It's just becoming that much easier to be able to collect and aggregate that data, especially with the ubiquitous storage capabilities of cloud-based storage. But the problem is that most of the data that's being collected is either being left on the floor or purposely being purged out of online experiences, online IT experiences. Sometimes we have to make tough choices. We have to make choices with respect to performance and cost. We can't keep exabytes of data online necessarily and put that in a warehouse, even if it is based on a hyper-successful platform, pick your technology of choice. There are choices to be made. And so when we talk about data lake, which is such a big buzzword, right? It's been a buzzword for a couple of years, but at the end of the day, I think we're moving past that. We're moving past data lake. We're now into galactic, planet-sized oceans of content. And it helps to think about data lakes in the context of where we're going in the future, which is almost ocean-sized collections of data. The interesting thing about this, though, is that there is this aspect of data that presents itself and is exposed and is online. It's manipulatable, it's discoverable, it's queryable. But that is merely the tip of the iceberg. This is the experience I see in working with many customers here in LA. I'm sure you can relate to this, because at the end of the day, there's an ocean of content beneath that is either left off in the archive or perhaps not even in the system, because we've had to make choices. We can't keep an infinite amount of data online, for example, in our warehouses. It's a cost and performance conversation. So we're almost going from the concept of big data, which is above the surface, to what I'm calling, and what you'll hear in the industry, is enormous data. We're now in that realm. The interesting thing to note about this, though, is that there's huge potential in this untapped section of content right below the surface of the ocean. According to the infamous IDC Digital Universe study in 2020, when we're talking about 44 zettabytes of content flowing throughout the interweb, a lot of that, up to 90% of that is dark. It's unstructured, it might be left behind, it might not be tapped. There's even the potential for, the estimates are upwards of nearly 40% of that could be gold. So what do we do about it? It would be really nice, and let's talk actual concrete implementation details. This is beyond theory. And because I have a little bit of a bias towards the Amazon platform, having been a citizen of that platform, but I also honestly do believe in the capabilities of that platform, so we'll use that as our example today. It would be fantastic if we could combine the powers of something like Redshift, which provides that low latency online experience for SQL-based interactive analytics, and combine that with the breadth and reach and storage capacity and throughput of something like S3. What if we had the power to create this uniform experience for our IT analysts, our data stewards, our stakeholders, our dashboards? What if we could create this concept of a galactically large, enormous data warehouse, a virtual data warehouse? That's the idea behind this. And we could build it today. It's actually possible. In April of this year, Amazon launched the latest iteration as a part of its family of analytic components called Amazon Redshift Spectrum. We'll talk about that, but let me just go quickly through some of these other big data key enablers that many customers that we work with adopt. For example, at the data processing layer, we have systems and services such as Amazon EMR, Elastic MapReduce, which is a managed Hadoop service. We have Amazon Redshift, which is a schema on read. It's a dedicated SQL-based MPP warehouse, massively parallel processing warehouse. It's a cluster of nodes that work together to provide a SQL BI type of experience. Amazon Athena is managed Presto, Facebook Presto, SQL as a service, clusterless, serverless from your perspective. You basically point your client at it, you submit your SQL, and it essentially carpet bombs S3 and pulls that data back. On this middle tier, we have other key capabilities, including Kinesis, which is Amazon's functionally equivalent managed Kafka. It's actually not based on Kafka. It's Amazon built it for themselves, and they turned it into a service. AWS Glue is an ETL as a service offering that's bound to be released soon. And then we'll talk a little bit more about Amazon Redshift Spectrum as that proxy from Redshift down to the lower levels of this architecture, the data lake storage, object storage, infinitely scaled, internet scale storage. Actually, we'll go ahead and just keep moving forward. Let's talk very specifically about these key building blocks. Amazon EMR, again, is a managed Hadoop platform. You basically identify the size of your cluster and the types of applications you want: Presto, Impala, Hive, Mahout, Spark, of course. And you press a button and launches that cluster. Great for those of you who are in the data engineering or data science field and want to be able to run with a managed Hadoop experience. For those who are more interested in committing to a data model and running SQL and running queries against a dimensional model or perhaps even a denormalized model, but basically having that committed data model experience, running reports and queries if you've got Tableau or a SQL client, Redshift is your candidate technology here. We have a lot of customers who run massively sized warehouses. It can go up to, I believe, 1.6 petabyte. And that's only what Amazon's tested. Technically, you can. I'm sure there's a path to adding more nodes to the cluster if necessary, but it may not be, because there's now a newly launched capability called Amazon Redshift Spectrum, which will basically provide you a proxy into an underlying managed fleet of compute nodes, which will be your agent in scanning and sweeping the underlying vastness of the S3 object store. Taking a step back real quickly, normally when we have these conversations with customers, it's usually a conversation of schema on read versus schema on write. I have a workload. I need to be able to do some data engineering, some data wrangling, some ETL, maybe some interactive analytics. Hadoop might be your answer. There's a lot of great things about Hadoop, especially the fact that it has native S3 integration built in from day one. or early on in the code base of the Apache code base. S3 was always a tier 1 citizen, just like HDFS. You could scale out Hadoop to n number of nodes very easily, a large number of data formats for interactive analytics or for data engineering, Parquet, ORC, RC files, JSON. Very popular with the developer, the big data developer community, of course. And on the right side, however, as we see more and more customers focusing in on getting that very dedicated SQL experience, I'm not necessarily interested in a dynamic sort of always discovering and poking around the underlying infrastructure. I know my data model, I have a dimensional model, I have a star or snowflake schema. I'm sourcing my systems from OLTP sources, and I want to put it out there and make it queryable. That's what Redshift's really good at. And it has years and years of optimization behind it. It's sourced from originally from a system called ParXL, and it has lots of it has a lot of production experience running massively scaled warehousing for many customers worldwide. So the optimization engine behind it is top notch. And I get sub-second typically. I mean, your mileage may vary, but the general idea is you can achieve sub-second response times, and it's really well tuned for things like dimensional models, join optimized. I wish I could have both. Wish I could have my cake and eat it too. And the good news is you can. So now there is this combined technology that brings the two worlds together, being able to have the best of an MPP SQL warehouse experience, riding on top of an infinitely large galactic-sized pool of content, S3 backed. This is called Redshift Spectrum. Redshift Spectrum, as you can see on the right-hand side, provides an integration experience from the top of the stack. BI/SQL client will connect with the underlying cluster, a Postgres interface. The warehouse will make decisions about what needs to be farmed out to an underlying hidden tier called the Spectrum tier. Spectrum is a number of nodes, a vast tier of nodes that Amazon manages, and it makes decisions about sweeping and scanning and doing predicate pushdown down to the underlying data lake. And it combines that data and filters that data back up the stack. Lo and behold, with this tech, we may be able to achieve this vision of a virtual galactic-sized warehouse, a virtual warehouse. Just a real quick note on what this looks like behind the scenes. If we were to submit a query, as I noted earlier, you're going to integrate or you're going to connect with the SQL client interface, the JDBC ODBC connection, provide a Postgres 8 compliant SQL submission. It's a subset of Postgres. But enough to get the job done, especially for OLAP, BI types of queries. The system will submit that to what's called a leader node. The leader node presents itself on the network, it intercepts the SQL, builds out an execution plan, and compiles it into native code, and then that is then farmed out to the worker nodes that are a part of the cluster. This is all local area network, 10 gigabit backplane. Those individual worker nodes then make decisions about whether to dispatch and do the work on local attached storage that's a part of each node, a little bit like HDFS data nodes, right? Similar pattern. But it also references metadata in this new important capability called the metastore, the meta catalog. It's not necessarily new for folks working with Hive. The Hive metastore is a critical component that helps the control plane in a big data pipeline figure out what needs to be done and where. In the new world, at least in the AWS platform, especially when we see AWS Glue launching a managed Hive metastore catalog that's supposed to be coming very soon, it's a very critical piece that informs all the moving parts of the ecosystem how to find data in S3. And so Redshift will use that to figure out where do I actually pull the data I need to pull, fact data, reference data. If it's sitting out in an S3 bucket, it will know how to route that request down the Spectrum. So the Spectrum nodes use that telemetry to figure out that roadmap. They use that to figure out what to do next. They then parallelize their work and pull data up and out from S3. Predicate pushdown, filters, aggregates, everything is done as far down, as close as possible to where data has gravity, so that we're minimizing the traffic flowing up. That's the beauty of this architecture. You could technically be running a very small baby micro-sized single node Redshift cluster as just the fake head and leveraging the beauty of this underlying platform. Yeah, think about that iceberg picture. So anyway, at the end of the day, results get aggregated back, they get filtered and pushed up into the cluster itself, joins and cleansing happens as normal. The leader node then presents the data back to the client. And we'll do a quick demo showing this idea. So I am going to work with a sample, small sample admittedly, but I think it'll get the point across, of using a dimensional model that's split between life having part of its life in what's called the online part of the architecture. It lives in Redshift. I might have the last 2 years worth of music streaming data stored in my Redshift cluster, so I could do very quick analyses to find out who's been listening to what parts of the world are listening to what tracks, what artists. For example, this is a music media use case, obviously. And then I might have the rest of that underlying lake or ocean in terms of the last 20 years worth of telemetry. I might have that archived off as CSV gzip files, for example. I might have that off with cheaper storage. There's no compute attached to it. I'm not paying money for it other than what it takes to store in S3, which is pretty cost effective. So this example is going to show Last.fm, an online music streaming capability or service. It's a sample data set where we have reference data sets in terms of user profile data up in Redshift. We have a subset of 20 million records stored in Redshift, representing the last few years of content or of subscribers and what they've been listening to. And then at the bottom of the lake in S3, we have the remainder of the last decade or the decade prior of content that was stored and captured as far as what people were listening to. The common join key will be user ID, and we'll be using Redshift as if it was just another day. For those of you who used Redshift or something comparable to it, it's just running my same exact queries almost as I would normally. I'm not having to retool or re-engineer my thinking very much. It's almost business as usual. And by the way, just in terms of the kinds of content we're talking about, like for someone like me, you know, back in the day, if you went far back enough in time, you'd see the kind of music I listened to. I've kind of matured a little bit. I think so. But yes, I used to think that was cool. Maybe it still is. All right. In terms of technology building blocks, what we're going to see here is examples of Redshift with dimensional data and fact data stored in the cluster. Spectrum provides that brokering feature and pulls the remainder of the offline archive fact data from S3, and it's using Catalog to support it, to help it determine where to go. And if we have time, I'll show a little bit of Athena, which is basically a parallel path through this whole structure. If I'm not already committed to Redshift, I have the potential to use SQL as a service on top of S3 by using something like Athena, which again is a managed Facebook Presto capability. The first thing that has to happen is we have to define or register the table data. We create a view of sorts, an external table that maps to data stored in S3. So in S3, I actually have content that represents older archived fact data. And so here we are in S3. I've got a couple of CSV files, gzipped. I've actually gone through an ETL process to convert it over to what's called per-K, which is a compressed columnar. Well, I'll use compression and I'll convert it to columnar format. The reason for doing that is it's a best practice when you're using these technologies. Once you get past that initial discovery and get past the point of playing around with the data, you want to compress it because you pay by I/O. So it makes a lot of sense from a performance and cost standpoint to convert it into a more suitable intermediate analytic format. But ultimately, think of these as CSV files or TSV files. They're just sitting out there in S3 and they're aging out. The directory for this is out on S3, and I basically create I register that using a catalog interface. In this case, we'll use Athena. Athena provides a Hive Metastore catalog interface. This will eventually, hopefully, become a single discrete service unto itself called AWS Glue. Glue will be a managed Metastore. I'll go into this. I'll issue my DDL that basically says create external table, provide the overlay structure. I'm not actually doing anything. It's a lazy definition, right? Not until we actually access the data through Spectrum or through Athena or through Hive or through Presto or through other technologies, that's not going to materialize. So until that point. So all we're doing is we're defining this view. We're defining a pointer to where it is on S3. I'll run this real quick DDL, and it gets registered in the system. You can see an example here of the schema, and I can actually sample the data set directly from this interface. So again, these are just, think of these as big, long fact tables that are just basically materializing either when Redshift Spectrum requests it or when some other technology like Athena requests it. So at this point, I'm going to shift gears and show you, after we've defined that table in S3, skipping a few steps forward, we would have loaded that into Redshift. A normal BI warehouse experience would have loaded that as a part of an ETL into Redshift. We'll load just the last 2 years or 3 years or 4 years worth of data, keeping that data hot, keeping it in the online Redshift cluster, and then we'll query it. And here's an example of some SQL that we use to query that online data that's contained in Redshift. Show me all the music plays organized by country over the last, let's say, 10 years. And I'll run that real quick right now using my SQL client. I'm using Aginity. This is a very popular tool that the community uses for interacting with Redshift. You can see I'm going out to Portland. The data's online. It's on Redshift. I have data that represents the last 10 years of information. But what if I need to combine data from back in the archive? What if I need to do a strategic analysis that combines fact data that's sitting on S3? Well, the good news is I can take that table definition that I created earlier, and I could use it in a join. And what that looks like is this. And we'll be sharing these slides, of course, but the red represents, this is a two-part query. We have a union. The first part of the query is going after tables defined in Redshift in the online cluster. And the second part, the blue pieces, are pointing to that virtual external table. The blue part represents that not yet materialized view. But when I submit this through Redshift, through my Postgres client, we're going to get a combined experience. And I'll show you what that looks like very quickly. So anyone have a timer? 1, 2, 3, 4, 5. There, okay. Not too bad, considering we're hitting, this is sweeping across local area network, wide area network, sweeping across 20 million records and doing this nice clean aggregation. And what would that look like visually beyond this kind of experience? Let me do this last view for you. So we could combine all of this in a tool of choice, whatever query-capable tool you have, whether it's Tableau or Domo. In this case, I'm going to use Amazon QuickSight, because it's cheap. I get paid $9, or at least my boss did. But here you are, materializing those queries together. So the first one shows me what the online results were. Grouped by country, these are the number of music plays over the last 10 years. That's hot data. But if I wanted to do a strategic assessment and find out how much of those plays covered the last 20 years or n number of years. So you can see the blue areas represent the results, the fact data that was aggregated using Spectrum, combined with data in the online Redshift cluster. That's the red piece. So Obviously a very powerful feature. We've achieved horizontal partitioning with very little impact to the SQL experience. Okay, so summarize. No child left behind. MPP warehousing folks in the room, you can participate in the big, sexy data lake conversation now. You can partake of the infinite capabilities of S3 storage. S3 is a massively scaled backend store. Upwards of, your mileage may vary, 80 megabyte per second per thread. Capable of storing trillions of objects today, peaking at over a million requests per second. Massive backing data store. And you could actually use that data lake hub as a hub where you can use extra tools or other tools to improve the workflow. You might start with Hadoop, you might use Athena, you might use Redshift, you might use all of them, and all of them sharing the same data. And Spectrum's pretty cool, so give it a shot, give it a try. I don't make money off of it, I promise you, not anymore. It's a great tech. So thank you, everybody. I'm going to stick around. If there's any questions, how much time do we have?
Yeah. 5 minutes.
Oh, we have 5 minutes. Yes?
What is your take on Microsoft Azure? I'm a Microsoft guy, so.
What's my take on Microsoft Azure?
Yeah.
I will be very honest with you, having been 5 years in the Amazon bunker, it's hard for me to comment. I don't have enough practical hands-on exposure to it, although every customer that I've ever worked with has good things to say about all these platforms. Each has its pros and cons. I couldn't tell you about the equivalent functionality, however. But I'd be happy to have a conversation or take feedback on that. Yes?
If all you had were objects in S3, what's the difference between Redshift, Spectrum, and Athena?
So the question is, if you have objects in S3, what's the difference between Redshift Spectrum and Athena? Good question. Both provide a SQL on S3 experience. I think the key difference is asking yourself whether or not you're already a Redshift adopter. If you already have BI and ETL and data warehousing workflows built on Redshift, Redshift Spectrum gives you a door into the S3 data without having to go through an ETL process. If you're doing the occasional data discovery or interactive analytics, Athena's a really decent serverless experience. Everybody's talking about serverless as a trend. It's a real trend. I just want to throw SQL at the platform. But both can be used in a complementary way. Yes, sir.
If you have business users who are used to using a dimensional model, and you have a lot of raw production extracts sitting in your data lake, would you recommend using this technology to build that dimensional model on the fly, or would you maybe do a transformation to get the data into a dimensional model?
So is the question, let me see if I can repeat the question. Is the question, with this technology, does it make sense to move to a dimensional model versus?
Let's say your business, it's already a requirement from your business users to have a dimensional model. So I guess the question is, would you build it on the fly as they need it, or would you do transformations? Is the technology beefy enough or quick enough to do transformations?
Yeah, it's a good question. So I'll just the question, at least for myself, so that I can make sure I understand it, is in situations where I have the opportunity to do this sort of lazy materialize on view, schema on read kind of interaction versus committing to an entire pipeline and then committing to a dimensional model and then exposing that through a warehouse, for example. I think there's definitely areas where they overlap. My experience has been for groups and departments and customer communities that are committed to getting repeatable results, nightly reports, regular KPI dashboards, those kinds of experiences should be codified. We've already committed to a data model. There's no variation or very little variation. You may as well take the extra step to codify it into a workflow and get it into the warehouse in a dimensional model, or even you can even do a denormalized structure in the warehouse. Redshift is that good. Back in the day, we had to create OLAP cubes and stuff like that, but because the hardware is so good, you can get away with a flat table or set of structures, or you can get away with storing Snowflake. But my bottom line recommendation is, if the workflow is such that it's repeatable and has SLAs and it doesn't change, then you may as well commit to the model and build it in the warehouse. For those where you have user communities like data science communities, which are more exploratory and ad hoc and looking at things at the edge, and where maybe the requirements aren't as firm, then using something like an Athena or a Spectrum or a Presto on EMR is probably a good option. I'm sorry, I think we're done. I'll stick around. We have members of the Agilicium team also here. Kind of obvious, you can see the shirts, big A. Thank you everybody for coming. I really appreciate it.